So these are going to be the notes for section 7.2 and 7.4. If at any point during the video you find that I'm going too fast, need to take a break, pause, whatever, you should know that you can rewind and pause as necessary. Alright, in any case, let's get started. Objectives, 3 things, take a second, read through it. You should be familiar with most of the stuff we're going to be going over right now. Just some details we have to touch upon. First thing, formation of an ionic bond. How do ionic bonds form? Well, first off, we have to look at how ions are formed. First bullet says that ions are formed by blank resulting in formation of a charge. Based on the context of this, you should be able to figure out that in the blank, ions are formed by gain or loss of electrons. Now, because the electrons have a negative charge, if an atom happens to gain a negative charge, it's going to get more negativity, so it becomes gains a negative charge. If it loses electrons, it's going to lose negativity, in other words, end up with a positive charge. Underneath that, it says the electrostatic force that holds oppositely charged particles together in an ionic compound is called an ionic bond. Here's what that's saying. If we look at an example, typically you'll see me use NaCl as a common example because that is really textbook simple ionic compound. How do we know it's an ionic compound? Well, all ionic compounds are going to start with a metal or ammonium. In this case, sodium is a metal, so we know it's going to be an ionic compound. Ionic compounds are going to be held together by what is known as an ionic bond. What's an ionic bond? Well, sodium is going to form a 1+ charge. And that's your sodium ion right there. And because this has a positive charge, it's going to attract negatively charged ions. In this case, it's going to be a chloride ion. As a result, when the two of them are attracted to each other, the force that pulls them together is referred to as an electrostatic force. And if you recall what the definition of a bond is, it's going to be the force that holds two atoms together. In this instance, because they are going to have negative and positive charge, that bond or force that holds them together is referred to as your ionic bond. That's all that is. Okay. Bottom line, opposites attract. Compounds that contain ions, thereby forming ionic bonds, are called ionic compounds. Ionic compounds can be identified because they start with metals or NH4, ammonium. You'll see that it's bolded, this sentence, because it's an important sentence. We're actually going to see a lot of this in the next chapter and see the relevance of that later on. So make sure you keep that in the back of your head. Okay. Otherwise, flip over, and this is actually going to be simply the bottom part of your handout. All right. Properties of ionic compounds. Let's see if we can get that guy a little bit more focused. No, not working out. There we go. Okay. The electrostatic force, blank ions with opposite charges. We just said that electrostatic force is what attracts ions with opposite charges. This attraction occurs in a 3-dimensional region. We'll talk about that in a little bit. The strong attractions among the positive and negative ions results in a formation of a crystal lattice. A crystal lattice is a 3-dimensional geometric arrangement of particles. So again, using example, sodium chloride, again. This represents sodium, this represents your chloride ions. If you look back at the first bullet, back down here, okay, this part here, it says this attraction occurs in a 3-dimensional region. This can be demonstrated by these 2 diagrams here. Let's look at the first one, top. If we look at just the sodium ion here, the sodium ion has a positive charge. It's going to attract negatively charged ions. In this case, it's going to be chloride ions. Now, this attraction occurs in multiple regions. It is not just going to attract ions next to it, left and right of it. It's going to attract negatively charged chloride ions that are above and below and in front and behind. So this force of attraction occurs in a 3-dimensional region. Okay. Left, right, top, down, front, and back. Now, you have to also imagine that every single one of these chloride ions is going to do the same. So let's change context. Let's take one of these guys, make it this one. These negative chloride ions are going to attract positively charged sodium ions. And this attraction is going to attract it in the above, below, left, right, front, and back orientations. Now, if you have the scenario repeating where we take one of these guys and put it in here and surround it, take one of these guys, surround it as such, you find that you're going to get a repeating pattern as demonstrated in this diagram. Each of these guys, in this instance, the center chloride ion that I'm pointing to is going to be surrounded by positively charged sodium ions. Okay, and each of these sodiums are going to be surrounded in turn by negative charge. This entire structure right here, that is what is referred to as your crystal lattice. So let's look back at the summary of these two bullets. The electrostatic force attracts ions with opposite charges. This attraction occurs in a three-dimensional region. We just demonstrated that here. The strong attraction among the positive and negative ions results in the formation of a crystal lattice. The crystal lattice is the three-dimensional, okay, you can see left and right, top and bottom, front and back, three-dimensional geometric arrangement of particles. So this entire thing is referred to as a crystal lattice. That's pretty much it. Okay, moving on to the next handout. So, melting point, boiling point, and hardness. All three of these characteristics depend on the strength of attraction. Okay, if you recall, melting is going to be the process where you go from a solid to a liquid. And if I were to demonstrate that for an ionic compound, here's your solid right here. We know it's a solid because you're going to have set defined edges, okay? And that force of attraction between the particles is so strong that even though this particle might want to tip over, the force of attraction by the adjacent ions are keeping it in place. That's why solids have a defined shape, because that force of attraction is so strong. Now, how do we get it from a solid to a liquid where it doesn't have defined edges, where the force of attraction is strong enough to keep them together, but not strong enough to hold them exactly in place? That's why liquids can take on the shape of their container. Okay, the way we can get that to occur is to weaken some of this force of attraction, or overcome it. How do we overcome it? We add energy, typically in the form of heat. We add energy. Okay, so on this table, I know you probably can't see it very well in the overhead. Every so often it might go in and out of focus, but you'll see, let's take a look at the extremes. Sodium iodide and magnesium oxide. The melting point for sodium iodide is 660 degrees Celsius. You'll see that it's going to be relatively high, okay? But even still, ionic compounds, due to the nature of their plus and minus attractive forces, typically have high melting points. That's what the up MP stands for. And if we take a look, you'll see that's demonstrated by sodium iodide. But even still, amongst ionic compounds, the melting points can vary. 660 degrees for our sodium iodide and 2,852 degrees for magnesium oxide. Okay, and even still with the boiling point, you'll see similar phenomenon. To boil it, in other words, to go from a liquid to a gas, okay, so boiling, going from a liquid to a gas, where this would be your liquid particles here. Again, force of attraction is strong enough to keep them together, but not strong enough to keep them in set rigid formation. And then you actually have to give it so much energy that you break that force of attraction. Now that's going to be relatively difficult for ionic compounds because these guys all have opposite charges. Some are positive, some are negative, and the opposite charges are going to obviously attract each other. Okay, so as a result, ionic compounds also have typically very high boiling points, as is demonstrated by here. You can see sodium iodide, boiling point is 1,304, and for magnesium oxide, you'll see that it's going to be even higher, 3,600 degrees Celsius. Okay, and if you haven't deduced already, you can figure that the force of attraction between the sodium and the iodine in this is not going to be quite as strong as the force of attraction between the magnesium ion and the oxide ions here. So, what dictates the strength of them? Okay, we're going to get to that in a little bit. All right, really it deals with size of ions, but again, as I said, we'll get to that in a little bit. Strength of attraction affects the hardness of ionic solids as well. This figure demonstrates how and why crystals break when an external force is applied. So let's take a look. This diagram is self-explanatory. You start off with an undisturbed ionic crystal. Positive surrounded by a negative. Each of these negatives are going to be surrounded by positives. Each of these positives surrounded by negatives, creating this crystal lattice. If an external force is applied, be it hammer to the crystal or you even dropping the crystal, etc., that's going to apply a force. It realigns the particles. Okay, and by realigning the particles, what happens is that, as you saw previously, you had alternating negative, positive, negative, negative, positive, negative, positive, etc. But when you realign it, okay, some of those particles, when you apply an external force, will realign so that you're going to have like charges adjacent to each other. As we know, like charges repel, so what happens is that they push each other apart. Forces of repulsion break the crystal apart. Now, what you have to realize is that at the absolute atomic level, when this is occurring, is that some of them will realign, some of them won't. When they do realign, and the opposites are like charges are adjacent to each other, they will repel each other. If they realign, but they have opposites next to each other, then they may stay in place. But more than likely, it is going to shift it and break it apart, because the moment that you have two like charges next to each other, they repel each other. Once they are repelled, it is difficult to get this negative back close to this positive to attract each other again. Okay? If that didn't make any sense, just, rewind and replay it as necessary. Okay. Otherwise, the energy required to separate 1 mole unit amount, like a dozen. Okay, we're going to get on this subject a lot more, I believe in chapter 9. Unit amount, like a dozen of an ion, is an ionic compound, is referred to as the lattice energy. In other words, if I have a certain amount of crystals of ionic compounds, the amount of energy that I need to separate that certain amount or mole is referred to as a lattice energy. Lattice energy is directly related to the size of the ions, okay? So that's a very important thing. Size of the ions that are bonded. It's not anything other than size of this. So you'll see the smaller the ion, the greater the attraction, okay? So smaller ions will hold on to each other closer, stronger than larger ions. Smaller ions form compounds requiring more energy to separate. Hopefully that makes sense. Okay, moving on. Ionic compounds and electrolytes. This is actually kind of an important point. Okay, as far as ionic compounds and electrolytes go, in a solid, ions are locked into position. Electrons cannot flow freely. Solid ions are poor conductors of electricity. What that means is, what electricity is basically the transference of electrons. So if you have a solid where you have a series of plus minuses locked in position, plus minus, plus minus, let's fix that, otherwise it's going to be confusing. Minus, plus, minus. As such, if you have a series of plus and minuses here, okay, you'll see that electrons cannot transfer across through this because of the fact that these pluses and minuses are locked into position. Okay, that's basically what the first bullet is saying. In a solid, ions are locked into position. Electrons cannot flow freely. Solid ions are poor conductors of electricity. Electricity flow of electrons, so if electrons can't flow freely, then electron is not conducted well. Liquid ions, or ions in aqueous solution, aqueous referring to water, water solution, have electrons that are free to move, so they conduct electricity easily. So what happens is that if I take the salt and I actually put it into water, what the water does is it actually separates it. Okay, it separates it, and instead of locking all the positives and the negatives together, it actually allows them to float around. And by having these particles just randomly float around, it gives the opportunity for electrons to start moving around. Alright, let's throw in a negative there. So what happens is that water, as I said, separates it. As being separated, what happens is that now electricity can transfer through. Okay, so solid ions, not very good with electricity. But if I were to do aqueous or dissolved ions, that is good for electricity. Okay, so in this diagram you can see kind of a cheesy picture, but you'll see that the positives are now able to move around, and you can see that this electrode has positive charge, so all the negative charges will be attracted to it. This electrode has negative charge, so all the positives can move around to it. And the reason why these ions are able to move to their respective electrodes is because of the fact that they're in water, as demonstrated by this guy. Okay, so that's the spiel on ionic compounds and electrolytes. Okay, so you can take an ionic compound. If it's solid, it doesn't conduct electricity, and if it's in water, it is able to. That's the bottom line. And once they are in water, these aqueous ions are referred to as electrolytes. So again, scientists loving to sound a little complicated. Okay, electrolytes are simply dissolved ions. That's all it is. Okay. All right, moving on.